This one is C6H12O. It has one double bond equivalent. We're looking at the pieces here. We see a 1H in the 9 to 10 region. Now that's usually going to indicate an aldehyde group because of where it is. But the other clue that it's an aldehyde group is also given by the fact that it's a single peak and it's not broad. Now if it was broad, you might be thinking it was an OH, maybe a carboxylic acid group, but since it's not, there's no BR, little BR designation here, we can assume that that's a straight peak that's not broad. So we're definitely more looking at an aldehyde grouping. Down here we've got a CH2 and then a 6H and a 3H, and the CH2 is fine, but this is going to be 3 CH3s. Now when deciding whether or not a 6H is going to be 2 CH3s or 3 CH2s, you can look at this guide here that I have, and what you'll see is that when there's one peak, two peaks, or three peaks under the 6H, it's most likely to be 2 CH3s, and when there's 4 peaks under the 6H, it's probably more likely to be 3 CH2s. So you can base your assumption on symmetry arguments, and if you'd like, you are more than welcome to stop the video and you can read the arguments I have here for why these kinds of groupings are generally indicative of 2 CH3 groups. So let's see, we've got those. Everything's counted down to 0 except for here, this one carbon. So that would be this carbon right here. We have all the pieces. Now we can put everything together. Now the 6H, because it's a single peak, is likely going to be 2 CH3s connected to the C like so. And these 2 CH3s are going to be adjacent to something that doesn't have any hydrogens on it, so this is the best thing that I can come up with for that. We have a CH2 grouping that has 4 peaks. That means that it must be next to a CH3. The CH3 in turn has 3 peaks, so it must be next to a CH2. So that arrangement would make a lot of sense. We can put the aldehyde grouping on the end here, and that should be our final structure.